The mole is a really difficult concept in chemistry, so we're going to try to make this more understandable for you by relating it to something you already know. The mole is actually a word that represents a number. So a dozen is a word that also represents a number, and it's a number you probably all know. It's 12. So just like a mole, a dozen represents a number. What about a gross? Do you know what a gross represents? A gross represents a dozen dozens, or 12 times 12, which is 144. So there's another word that represents a number. This last example, a ream, if you've ever bought a ream of paper or seen a ream of paper, it's one of the packages of paper. And a ream of paper contains 500 sheets of paper. So another word that represents a number. So a mole also represents a number, but it's kind of a difficult number to represent. It's a huge number. It's actually 6.02 times 10 to the 23rd. It's a huge number. If we were to write that out, it'd be 6 and then 0, 0. So that's 2 of the zeros, or 0, 2. That should be a 2. And then let's see, that's 21 more. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So that's a giant number. I couldn't even tell you in word terms what that represents. It's a huge number. We use this number because when you have exactly 1 mole of a substance, its mass will be the same as its GFM, or gram formula mass. We use this number to represent atoms. You can have a mole of copper. We use this number to represent molecules. You can have a mole of water molecules. And we can use it to represent compounds. We will make the distinction a little later on between molecules and compounds, but essentially salts, anything with a metal or a nonmetal, we can't call a molecule, we have to call it a compound. So we can also use this to represent an amount of compounds. Moles can also represent gases. 1 mole of any gas, and this is a question we often see on the Regents exam, at the same temperature and pressure. So it could be at standard temperature and pressure, or it could be at some other temperature and pressure, but as long as you have the same temperature and pressure, any gas will have the same volume as another gas. Will occupy the same volume. And that volume, in case you're wondering, is 22.4 liters. You don't actually have to know that. You just need to know that an amount of a gas, if you have the same amount of a gas at the same temperature and pressure, will have the same volume as another gas at the same temperature and pressure. What would the mass of 1 mole of the following be? Well, we said we defined the mole because at 1 mole, at that number of molecules, atoms, or compounds, you're going to have the mass that is the GFM. So really all you're going to do is you're going to figure out the GFM for each of these. So copper, we're going to look that up in the periodic table. So here's our periodic table. And then right here is copper, and again, we're going to round that to 2 decimal places, so that'll be 63.55. So a mole of copper will weigh 63.55 grams. So if I told you, hey, go in the back and mass me out 1 mole of copper, all you do is mass out 63.55 grams. We can do the same thing for aluminum then. 1 mole of aluminum will have a mass of 26.98. We're going to ignore those other decimal places. So 26.98 grams. All right, so those are both atom examples. Water is going to give us an example of a molecule. So we have H2 H2O is the formula of water. So we got to add up the masses of each of those elements. Hydrogen happens to be right here. When we round that to 2 decimal places, it's 1.01. So we're going to do, and there's 2 of them. I'm going to do that math in your head. It'd be 2.02. And then we have to add the mass of oxygen, which is over here. And when we round that to 2 decimal places, it ends up being an even 16. So adding that up, the mass of water is 18.02 grams. And that's actually a mass you're going to use quite frequently. Don't think yourself a geek if you memorize it, but we'll all call you one anyway. All right, moving on to the next example. Sodium chloride is actually a salt. So this is going to be an example of a mole of a compound. So down here, I know it's pretty small right here, but we have 22.99 for sodium. So 22.99. And then we got to add the mass of chlorine, which is over here at 35.45. And we add those up, and we're going to get 58.44 grams. So if I told you to go mass me out a mole of sodium chloride, you'd mass out 58.44 grams, which is actually quite a bit. All right, on to the next one. The next one happens to be a molecule. So here's another example of a mole of a molecule. This one is glucose, so C6H12O6. So we got a lot of math to do to figure out the GFM. Carbon down here is 12.01, and we need to multiply that by 6. So I'm going to do that off to the side here, and that works out to be 72.06, and then hydrogen is 1.01 times 12 would be 12.12, and then oxygen we said is 16. We'll multiply that by 6 and we get 96. So we need to add all that up, 180.18 grams. So if I said go get me a mole of glucose, you would go and mass out 180.18 grams. And in that sample that you've just massed, you would have 6.02 times 10 to the 23rd molecules. All right, our last example here, sodium hydrogen carbonate. This is actually an example of something with 2 types of bonding in it. Whenever you have a polyatomic, you have 2 types of bonding. And this is actually baking soda. So we're going to need to add up all those atoms. And this one's going to be a whole lot of math too. Sodium we said was 22.99. Hydrogen is 1.01, carbon is 12.01, and then we have 3 oxygen atoms, so I'm going to take 16 and multiply by 3, and I get 48. Add all those up, and we get 84.01 grams. So if I needed you to get me 1 mole of baking soda, you would go and mass out 84.10 grams. Now, do you imagine that each of these looks the same? So if you were to see these samples as 1 mole, would they look the same? The answer is no. They wouldn't have the same volume. They wouldn't have the same mass. But what is common with all of these examples is the number of molecules, or in some cases, in our 2 element examples, the number of atoms. So the mole is a really useful number because we know exactly how many of the atoms or molecules we have when we mass out that amount. All right, let's see if we can do some examples where we calculate moles. In calculating moles, we can actually use an equation that's on the back of your reference tables. So we're going to reference table T now. So here is table T, and on table T, you're going to see the second one down here is a mole calculation. So if you want to figure out how many moles of something you have, typically you will be given a mass. So they'll say, hey, I have 5 grams of something, and then you will need to calculate the gram formula mass, just like we did in this section right here. All we did was calculate the gram formula mass. So you're going to take the given mass, the mass they've given you, and you're going to divide by that gram formula mass. And that will give you the amount of moles of that substance that you have. So let's try an example. Let's say we had 27.50 grams of copper. So that's our given mass. So using the equation in the moles calculation down here, moles is equal to our given mass in grams divided by the GFM. So our given mass was 27.50 grams, and we need to divide by the GFM. So if you've forgotten, in order to figure out the GFM, all you're going to do is look at your mass in the periodic table. For this one, since it's elemental, we're just going to use this mass. We don't have to add or multiply anything to figure it out. So it's just 63.55. 63.55. Now the units for GFM are actually grams per mole. So and we abbreviate by leaving the E off. I know it's weird, but at least it's something. So if you're following along with the math here, you can do the same thing with units that you do with numbers. So you have grams over grams. Those are going to cancel each other out. And you'll be left with 1 over mole. And in order to solve for that, and I'm going to do this off to the side, you have 1 over mole. So to get that out of this bizarro fraction, and I'm sure there's some name for it in math, you would need to multiply by the inverse. So I'm going to multiply the top and the bottom, because whatever you do to the bottom, you have to do to the top and vice versa. Mole over 1. And then do the same thing above. Mole over 1. And then your moles cancel in the denominator and the ones cancel out, so you'll be left with moles. So that's how this equation works, that it's actually going to end up being in moles. It's good to understand that when you get to physics. So we're going to do 27.5 divided by our GFM, which is 63.55, and you're going to get 0. And if we're using sig figs, it should be 0.4327 moles. And that's our answer. Math is easy. Concept is kind of hard. All right, let's try another example. We're going to try this with aluminum. So let's say we have a sample of aluminum that is 5.25 grams. How many moles would that represent? So again, we're using our moles equation. Moles is equal to given mass over GFM. Our given mass is 5.25 grams. And then we need the GFM of aluminum. We looked it up a little bit ago, but just to remind you, it's right here. Aluminum is going to be 26.98. So I can move that. 26.98, and the units are grams per mole. And now we can calculate 5.25 divided by 26.98, and that's going to give us 0.19. I mentioned sig figs a few minutes ago. Essentially, when you look at your numbers, you're going to use the least number of numbers. So this has 3 numbers in it, this has 4 numbers in it, so our answer is going to have 3 numbers. So when I round, you're going to end up with 0.195 moles. Sig figs are a bit more complicated than I just explained, but that'll work for now. Let's try some more. So this is an analogy that I've used in the past, because now that we've learned how to calculate moles, we need to apply that to actual chemical reactions using equations. And it's kind of like a recipe. A chemical reaction is kind of like a recipe. Here's my recipe for pancakes. By the way, I don't think this would actually work, but it's good enough. So we have this recipe. We need 1 large egg, a cup of flour, 3/4 of a cup of milk, a tablespoon of oil, 3 teaspoons baking powder, and 1/4 of a teaspoon of salt. And the yield on this recipe is 9 pancakes. So let's say that instead of making 9 pancakes, I wanted to make 27 pancakes. In that case, how many eggs would I need? I got to go check my fridge to make sure I have enough. So you're going to look at your yield. I can normally make 9 with this recipe. So if I want to make 27, I'm going to have to triple my recipe. So each of the ingredients in this list is going to get tripled. And that means I'm going to need 3 eggs. Next question, how much baking powder would I need if I made 2 batches? So they're telling us we're doubling our recipe. So in our typical recipe, in a 1 batch recipe, we need 3 teaspoons of baking powder, but if we double it, we're going to need 6 teaspoons. And the last question relating to this is, if I have a cup and a half of milk, so that's all the milk I have, how many eggs would I need and how much baking powder would I need to use all the milk? So I can only make what I can make if I have a cup and a half of milk. So when we look at our recipe, a normal recipe is 3/4 of a cup. So what would I have to do to the recipe in order to make it a cup and a half? Well, it would just be doubling it. So once again, we're going to double. My baking powder, when I double it, will be 6 teaspoons. And my eggs would be 2 eggs. And I want you to think about this analogy as we go through an example of an equation. An equation is really just a recipe. So on the left here, we have all of our ingredients, and on the right is our product, our 9 pancakes. So what are the ingredients in our reaction? Well, we need hydrogen and we need nitrogen. And we're going to end up making ammonia. Moles are actually these units represented by the coefficients. It's a ratio. And I can't compare hydrogen to nitrogen really, because they may have different densities. They might have, actually as gases I could, but they may have different masses and things like that. But I can compare the number of molecules. So I'm going to compare using these coefficients. So if I had 3 molecules of H2O, I would need 1 molecule of H2 and 1 molecule of N2, and I'd end up with 2 molecules of ammonia. Or, since moles is a number, I could just use moles. So if I had 3 moles of H2 and 1 mole of N2, I'd end up with 2 moles of NH3. So in this reaction, how many moles of hydrogen would be required? 3. And nitrogen, even though there is no coefficient, we know it's a 1. And then how many moles of ammonia, that's our product, will be produced? And that would be 2. Question F, how many moles of hydrogen are required to make 6 moles of ammonia? So they want to know how much hydrogen we would need if we're going to end up with 6 moles of ammonia. So what would we be doing to our recipe in order to end up with 6? Well, we'd be tripling it, right? So if you tripled your hydrogen, you would have 9 moles of hydrogen. Letter G, how many moles of ammonia can be made with 4 moles of hydrogen? Ooh, this one's not as easy. So this one you might not be able to do in your head. So I'm going to show you how to set up a proportion. So instead of 3, which is our normal proportion, we want to know if we had 4. And they want to know then how many moles of ammonia we would make. So really our proportion is 4/3, or ratio, or whatever you want to call it. I don't know what they call things in math anymore, over 2. So then we're going to solve this. A lot of times, especially if the x is in the denominator, students have a hard time with this. I'm going to show you the long way, and then I'll show you the short way. So typically when you have 2 fractions set equal to each other, you can go ahead and cross multiply. 4 times 2 is 8, is equal to 3x. And then to get x alone, you're going to divide each side by 3. And you'll get x is equal to 8/3. And then, of course, we don't really like fractions, so we're going to do the math and do 8 divided by 3, and you get 2.7-ish. So we're going to end up with 2.7 moles of ammonia. Now, the fast way is where you don't actually do all of the cross multiplying. Let me show you what that looks like. And we're going to end up with the same answer, you'll see. This is the super lazy chemist method. So we said we would have 4/3 is equal to x/2. So I want to get the x alone. And what you can do, and don't tell your math teachers I told you this, they'll probably hate me for it, but you can actually just cross multiply those 2. Don't do the x times the 3. If you just do the 4 times the 2, you're going to get x alone. Watch what happens. 4 times 2 is 8/3 is equal to x. Didn't we just get that in like 3 steps? So now when you do 8 divided by 3, you get 2.7 moles. Look at that. Faster, less mess, You don't have to do it that way. If you want to do the full cross multiplying, go for it. Last question here is probably the hardest. How many moles of nitrogen are required to make 51 grams of ammonia? Now, I can't compare grams of nitrogen to grams of ammonia. It's not possible. So I can, however, compare moles of nitrogen to moles of ammonia. And that's actually what we did in letter G in that last example. This time we're going to do it, but we're going to do it with nitrogen and ammonia first just as moles. So normally the coefficient on nitrogen is 1, okay? And the coefficient on the ammonia on the product side is 2. Okay, so all I did was take the coefficient from nitrogen, set it equal to the coefficient for ammonia. Now that's the normal ratio, the normal proportion of nitrogen to ammonia. Well, we want to know then how many moles of nitrogen. So this side, the left side here, is representing my nitrogen. And on this side, I'm going to represent my ammonia. In my question, it's saying 51 grams of ammonia. Well, I need that as moles. Do we have a way to do that? Do we have a way to convert grams to moles? Absolutely we do. So I'm going to need to do another step here before I can fill in the number here for my moles of ammonia. So I'm going to use my moles equation. Moles is equal to given mass over GFM. My given mass from the question was 51 grams, and then I need my GFM for ammonia. So we got to figure out the GFM for ammonia. The formula is NH3, so we're going to add nitrogen's mass, which when you look in the periodic table is 14.01, to 3 hydrogens. Hydrogen is 1.01 times 3 would make it 3.03, and you're going to end up with 17.04 grams. So our GFM is 17.04 grams per mole. And when we calculate that, you're going to get 2.99 moles. So that's the number that's going to go here. And now we're going to solve this equation. Again, you don't have to cross multiply everything, and I'm not going to. I'm just going to cross multiply the 1 times the 2.99, which you don't really need to do, but 2.99 then divided by 2 is going to give me, I'm going to write this over here, 1.5, I rounded, moles. And that's moles of ammonia. And that's our answer. That's the hardest kind of question you could possibly be asked. Be sure you try the practice problems we do in class, and please, please, please ask questions if you are struggling.